Alright, welcome to FRQ number 4 for set number 7. Okay, let's see. So we're given a table. This is for a spring. Alright, let's get to it. So it says, for part A, it says which quantities should be graphed in order to yield a straight line whose slope could be used to calculate a numerical value for A. And it tells us, it gives us this equation right here for force, and it has A in there that it's talking about. So if you would notice that this force equation that it gives us is Hooke's law, and A is our K. So we know when graphing Hooke's law, you graph your F and K, or X squared. So those are the quantities that should be graphed. Okay. So now it wants us to calculate any quantities, my goodness, that are missing. Okay. So we have our F, we have X, but we don't have X squared. So we're just gonna go ahead and that's what we're gonna find. We're gonna find X squared. Oops. Okay, so this is pretty simple. We're just gonna square all of these values. Okay, so that's part B. Let's see, part C, using the grid below. Okay, so now we're just plotting. Okay, so part C. Okay, so we're just gonna plot these two columns. So F is gonna be on your y-axis, X squared will be on your x-axis. Okay, so let's go ahead. Okay. Let's see. Looking at this, I realized I kept doing that throughout this. I kept writing them without their zeros. Did that there too. Okay. So, just gonna plot these. trying to write these as clear as I can. It's hard because it's a small space. Okay, so now we can just go ahead and plot these. Okay. Grab a ruler, draw a line that best fits. Actually, we don't have to draw a line, just says to plot. Okay, moving on then. Okay, so part D, part D says using our graph, calculate A. Okay, so it tells us that, gave us that function. So to find A, that means we're gonna be dividing. Okay, so you kind of just pick a spot. I'm gonna go with this second data set right here. So that's gonna be 17. Okay. And like we already discussed, our A is our K. So units for that is newtons per meter. Okay. dE. Okay, it wants us to calculate the work done by the, okay, so now it gives us a little scenario. It tells us that now there's a cart attached to the spring and it has a compressing maximum distance of 0.1 meters. Okay, so it wants us to calculate the work done by the cart in compressing the spring 0.1 from its equilibrium length. Okay, so we have F, okay, right, and we know that we can integrate to get work. So when you integrate, the little trick is you add an exponent, and then whatever this new exponent is, that's what you divide the coefficient by. So that's going to be 3, so it's 1,700 divided by 3. And now it's x cubed because we added. Okay, so now we just plug in that x that it told us. Oops. Okay. Oops. Went around. Okay, so you get 0.57 joules for work. Okay, and F. Calculate the speed of the cart just before it strikes the spring. Okay, so what we're going to use here is the work kinetic energy theorem. So that's going to be KE, changing KE is equal to KEF minus KEI. There is no KEI because it starts from rest. Yep, starts from rest. It also didn't, yeah, it starts from rest. I don't even know what I'm trying to say. Okay, so we're just gonna expand this 1/2 mv squared. The mass is 0.5. Good. Let's just solve for BF. Alright, that is the speed. And that concludes FRQ number 4. Again, we had parts B and C on the paper because it provided us the graph and the chart.